Last time we developed the histogram of the lifetimes of the bulbs, and the graph was like this. So we have the frequency decreasing for the higher value of the operational times. So then we normalize the frequency. So relative frequency means frequency of a class divided by the total number of objects that have been tested. So 100 was the number, and I divided all these values by that number 100, and the sum equals to 1. So this representation, this calculation, relative frequency, is important in statistics because it has normalized the frequencies. So now you can compare these values with the other experiments on the same objects. So now a better representation is that you take the mid values of the bins. So I define here X mid values, or we call it class mark. It's the central value. So the first one is equal to 100. Okay, 100 plus 0, because it started from 0 and it goes up to 100 months. So it is 50. Then here I define for the second class the mid value, which represents a lifetime from 100 to 200 at F19 and divided by 2, and so on for the rest of the classes. I pick up the same numbers, frequency numbers. The frequency numbers, and copy these numbers and paste them. So numbers have not been printed correctly because there was a calculation performed in those cells. So I have to paste those values in a specific paste special option, and that is paste only the values, and that's it. So total number, if we like to check it, total number of the objects, it was 100, right? So then we compute the relative frequency. I call it relative frequency. It is equal to the class frequency divided by the total number of experiments, n, and n is at $41. Okay, this number. When I drag this calculation, when I drag the cell to apply the similar calculation on the lower cells, so it will fix the value n. This was the n. So now the total number here is equal to the summation of all these values, and it equates to 1. So this is a famous representation that we now identify these numbers as probabilities. Probability that the new bulb taken from that company will perform up to 100 months, it is 0.7. Probability that a bulb taken from the company will perform to 200 months is this one, right? So it is 0.2. So they have a representation in probability, and now we can plot them. Again, I select a plot, okay, as a bar graph. I do not like these values. They have been automatically selected. So I have to select the appropriate one. Add series values must be taken from this column relative frequency, and the labels, I prefer the mid values of the classes. Okay, but to make it more uh, professional looking, so I have to format the data series. So there is a gap width, right? So if I reduce that one to say 1%, so now it is more attractive and informative representation that this one, this frequency, this relative frequency or probability belongs to the time values from 0 to 100. And then we have the next one. Well, there can be, you can explore further options that you can represent them with the different colors. Now, this relative frequency, if the variable, in our case the lifetimes, if the variable is a discrete variable, then up to this representation the graph is complete, the information is complete. Well, we have to add the axis titles. This is known as probability mass function, PMF. So as a matter of information, I add the axis title for vertical axis. For vertical axis, as this is the PMF, probability mass function representation, right? And in probability theory, we have certain models for which we can write the equation for probability mass functions. For x-axis, it is the same as the lifetimes. Lifetimes, months. Well, we see that our variable was not a discrete variable, right? Our variable was a continuous variable. Therefore, to come up with a better representation, we will further convert it to a density function. So a density function, in this case, it will be equal to the relative frequency divided by the class width. Right? So over here we have the class width equal to 100. There is a coincidence in our example that the total number of objects and the class width, they are equal. Numerically they are equal. So please keep this distinction. This 100 represents the class width. So this is the density. And I repeat all these calculations. And then now we would like to draw a continuous function. Insert. And now I take xy scatter. Select the data. X values again be the lifetime values, and y values will be the density values. So this one with the x-axis as lifetimes, and on vertical axis we have the variable, we have the vertical axis as the density function. So this is known as probability density function. The density has been computed from the probability mass function. So here is an analogy that density is equal to mass divided by the volume, right? So the if you have only one axis, then the volume is the length, right? Equivalent, or you can say analogous, is the length. So again, to make the graph professionally looking, we have to add the axis titles. X-axis is again the lifetimes, in months, and for vertical axis this is now probability density function, PDF, and it is represented by f of x. It's a continuous function. Now you are allowed to draw a smooth function through these points, right? For continuous variable, this is possible to draw a smooth function through probability density function, and you can develop its equation so that equation represent the whole story of the experiment. All the 100 values, they can be characterized by that equation. When you have the probability mass function for discrete variable, in that case you are not allowed to join the points, right? So please keep the difference in mind. Probability mass function is a representation for discrete variable, and probability density function is a representation for continuous variable.